Hey there, Calc folks. Back here with another lecture video in my series of lectures here on integration strategies, right? Integration techniques. We've looked at a couple of integration techniques up to this point. We've looked at integration by parts, and we've looked at trig integrals. Trig integrals is going to help us in our next technique. What we're going to look at next here is trigonometric substitution, folks. This technique known as trigonometric substitution. And what we're going to see happen in trigonometric substitution is we are going to perform a substitution, a lot like U substitution, but instead of substituting in a value in an expression in our integrand with the value of U, we're going to replace the variable in our integrand with some trigonometric function. And this is going to lead to, in some unique cases, simpler forms, simpler integrations. All right? A lot like U substitution does in its process. It performed correctly. It yields a simpler integration in the end. All right, we're going to see that happen with trigonometric substitution. But I will tell you, the integrals we're going to have to integrate are going to be trig integrals. Right, are going to be integrals of the previous material in some regards, in some cases. All right. Let's jump right into it. I don't have a long lecture for you here, folks. I have a couple of examples as well as the notables, and we'll look at these items. I do start off with the case of considering the integral given here, the integral of the square root of 1 minus x squared dx. All right. That square root does not distribute across those two terms. Keep that in mind. This is not just 1 minus x in value for an integrand. All right. If you were to expand 1 minus x squared, it would actually expand into, 1 minus x times 1 plus x in value, which does not simplify underneath the radical. All right. Currently, we don't have any real way of integrating this. If we try to use substitution, we don't have an x that's going to come about when we let u equal 1 minus x squared. All right. U substitution won't work very nicely here, if at all. Instead, what we apply is what's known as trigonometric substitution. Now, what is trigonometric substitution? If I take note here, we are just going to substitute in for the value of our variable x, right, a trigonometric function. Right? There's going to have a whole bunch of implications from that substitution, but it should, if we perform this correctly, simplify our integrand. Now, if done correctly, what we would consider doing here is letting x equal the sine of theta. That works conveniently. Letting x equal the sine of theta will end up implying that dx d theta equals the cosine of theta, or that when we think about the value of dx, the value seen here in our integral calculation, that could be said to be equivalent to cosine theta d theta. Right? That is the first implication that would come about from letting x equal sine theta. But it also implies that this would be true. That this quantity underneath the square root symbol, 1 minus x squared, would be 1 minus sine squared in theta, where from our Pythagorean identities for trigonometry, we know 1 minus sine squared theta is equivalent to cosine squared theta, which would be very convenient underneath that radical symbol. The square root would cancel with the squaring on the cosine. And in fact, that is the simplification that we begin to see. If we do the substitution in this case, all right, letting this x be the sine of theta makes the 1 minus x squared into the cosine squared theta underneath the square root symbol. And then as we had noted, the dx, the value of dx seen here, is going to become cosine theta d theta. So we substitute out this dx with cosine theta d theta. And the square root of the cosine squared becomes cosine theta times this cosine theta simplifies now to the integral for the cosine squared theta d theta. Where what we have there is a trig integral. And our rules from trig integrals tell us, right, tells us what? Apply the half angle formula. Cosine 2 theta is 1/2 the quantity 1 plus cosine 2 theta. Half angle formula. If we apply that here, that can be written as this. 1/2 times the integral of 1 plus cosine 2 theta, where that integral will distribute itself across these two terms. This will become theta. This will become 1/2 the sine of 2 theta. So we'll have 1/2 times that result, which will produce in the end 1/2 theta plus 1/4 sine 2 theta plus c. Now, that is not my final answer. A lot like U substitution, this answer is being presented, this antiderivative is being presented in terms of theta. Where initially, my integration is in terms of the variable x. I need to take that integration result in terms of theta, this antiderivative in terms of theta, and rewrite it. Rewrite it into a result that's in terms of x. And a lot like what happened back in U substitution, I'm going to rely on the fact that x equals the sine of theta. Right? That had all these initial implications that we saw, but it also has all these results, respectively, with respect to how theta relates to x. Right? In terms of x, since x equals sine theta, first of all, that will imply that theta will be the sine inverse of x. To solve that for theta, to obtain this result for theta, I'd have to solve this x equals sine theta for theta. And I do that by using the inverse sine function. Apply that to both sides, I end up finding theta is equal to the sine inverse of x. So that is going to be substituted in here for theta. Whereas for the sine of 2 theta, we rely on double angle formulas just to note that the sine of 2 theta is equal to 2 sine theta cosine theta. Where furthermore, if we take note that the sine theta is equal to x, right, implies from right triangle trigonometry that the cosine of theta would be equal to the square root of 1 minus x squared in value. Note this reference triangle supports all that. If the sine of theta is equal to x, that does imply that what we have there is the sine of theta equal to x over 1. And what do we know about sine of theta? It's opposite over hypotenuse in value. So if I'm thinking of a right triangle where I see this behavior happening, theta being this angle measurement, opposite side would be x in this result. Hypotenuse would be 1, meaning my adjacent side would measure the square root of 1 minus x squared from the Pythagorean theorem. So if I think about what would be the cosine of theta then, well, that's going to be my adjacent side over my hypotenuse. Right? The cosine of theta, which would be equal to your adjacent side over your hypotenuse, would be equivalent to 1 minus x squared in value. or the square root of 1 minus x squared in value. This result's seen here. All from putting this adjacent side over this hypotenuse, and the adjacent side's measurement coming about from Pythagorean theorem. I can substitute x in for sine theta. I can substitute the square root of 1 minus x squared in, square root of 1 minus x squared in for cosine theta. And those 2 times those quantities will get substituted in for the sine of 2 theta in the above result. And thus, in terms of x, we prepare this result seen here. Thus, in terms of x, that initial integral, which we saw was this result for an antiderivative in terms of theta, will have this theta replaced with the sine inverse of x. So that will become 1/2 sine inverse of x. Plus, we had 1/4 sine 2 theta. Did I cancel correctly here? The sine 2 theta is going to become 2 sine. I think we need to go back down to 1/2 there. Oh, wait, that would be 1/4. But down here, that should become 1/2. Right? Because it's going to be 2 sine theta cosine theta taking its place. That is getting substituted in there. And that'll cancel to 1/2. The sine of theta will become x. The cosine of theta will become the square root of 1 minus x squared in that result. Yep. So that, I do have to fix that fraction. And I did that. Right? But this would be then our result in terms of x from a little right triangle trigonometry. Which would make sense if we're doing trigonometric substitution. There's going to be some trigonometry mixed into this entire calculation. And there is with this reference triangle. All right. Now, what I do highlight here in the notes, folks, you can read through these. All right, calc, folks. If you read through this, all right, it will tell you that the above process illustrates what we call trigonometric substitution. What we, excuse me, what we had done above in our work here, starting at letting x equal the sine of theta in this calculation, substituting in with all of its implications, performing our integral with those implications implied, and then reversing that antiderivative result using some right triangle trigonometry to develop our final result in terms of x, right, are all examples, well, is an example of what we call trigonometric substitution, right? Substitution in this manner works rather conveniently when our integrand involves one of 3 cases. Where in these cases, a is any real number except for 0. Right? And we could have the case of an a squared minus an x squared, or an x squared minus an a squared, or an x squared plus an a squared in value, in form. The above example that we worked through, actually I can see it down here and compare the two. The above example seen right here, I do note down here, right, involves this integrand 1 minus x squared. Where if you compare it to one of these 3 cases, that aligns itself here with the first case, where you have a number minus a quantity of x squared. That's different than an x squared minus the quantity of a number, or x squared plus the quantity of a number. We have here in this case a squared, or a number, minus some quantity of x squared. Here it's 1 minus x squared. Here in our case, we went simple with a equal to 1, but a could have been more complex. All right. The technique is described down here below. All right. In each of these cases, we have a technique involving a trigonometric substitution, where these techniques are summarized as follows. And what we just did was case 1. Right. In case 1, we let x equal a sine theta. I let x equal 1 times the sine of theta in my previous example. That's where I started. That did imply dx was equal to cosine theta, and that did imply that 1 minus x squared was cosine squared theta, which are the following noted implications. This does imply that a squared minus x squared will be a squared cosine squared theta, and this does imply that dx will be a cosine theta d theta, where in my case a was 1, so this was 1 minus x squared was cosine squared theta because a was 1, and dx was equal to just 1 times cosine theta, or just cosine theta d theta in value. And then also, because I allow x equal to a sine theta, in the end I'm going to need to have some right triangle trigonometry to reference. And if sine theta is equal to x over a in my implication here, where x equals a sine theta in my substitution, this is the reference triangle that I develop that describes that entire trigonometric relationship between x, a, and the value of theta, which allows me to explore all my other trigonometric functions or relationships in terms of x. Right. Now that's for a squared minus x squared. That was the first case. Here's the second. Case for x squared minus a squared. In that case, you let a or x equal a secant theta. That has the following implications. X squared minus a squared will be a squared tangent squared theta, and dx will become a tangent theta secant theta, as noted here initially. And then having x equal a secant theta will also imply secant theta equals x over a, and gives us this following reference triangle seen down here, which will help me write my final answer in terms of x for this particular case. And then third case was that case of x squared plus a squared, and here is the substitution that I'm given and its implications. All right. When x squared plus a squared is your involved form, you let x equal a tangent theta. X squared plus a squared then will become a squared secant squared theta. Dx will become then a secant squared theta d theta. And the tangent of theta equal to x over a will have the following reference triangle relating x and a to theta in all of our trigonometric relationships. All right. Trig substitution, folks. It's these three cases you have to watch out for. Here is the approach summarized for each of the three cases. I illustrated the approach in our first example for case 1. I have one more example for you. To keep this brief, we'll look at some more examples in class. But we might consider the integral for 1 over the square root of x squared minus 4 dx. What case does that match? If we go up to our cases, you should recognize that that fits into case number 2. You have an x squared minus an a squared form. That's seen right down here. X squared minus 4 in our denominator under that radical is an x squared minus an a squared form, where a is equal to 2. So our strategy is what's told to us right in here. This is what we have to know. X is going to be a secant theta. A is 2, so x is going to be 2 secant theta. So x squared minus a squared will be 4 tangent squared theta. And dx will become 2 tangent theta secant theta d theta in my integration. I can perform that with these substitutions. And I do make note of that. This is an example of case 2. All right, x squared minus a squared, where a equals 2. And we're going to let x equal 2 secant theta. That does imply x squared minus 4 is 4 tangent squared theta, and implies dx is equal to 2 tangent theta secant theta d theta. So if I substitute that in, it follows from trigonometric substitution that I would prepare this statement, which does turn into this statement where you can see there's some convenient simpling here. The 2 tangent theta cancels in both the numerator and denominator. That will leave me the integral of the secant theta d theta, which is a fundamental rule presented back in the table at the beginning of the chapter in section 8.1, which says that's nothing more than the ln of the secant theta plus tangent theta. Absolute value. Now that solution is in terms of theta. How do I get back to x? That is where this reference triangle comes in. We have one for our case where a is 2, right, in the setup. So what I say down below here, the secant theta, since x equals 2 secant theta, we know this is automatically going to become 2. But since it also involves tangent theta, tangent, in this case, is opposite over adjacent. It's going to be the square root of x squared minus a squared over a. A is 2, so it's going to be the square root of x squared minus 4 over 2. Or 1/2 the square root of x squared minus 4. And thus, the integral that we were interested in, which presents itself in this format in the trigonometric substitution, will return to this statement using the above substitutions. X will become, well, I should say there, secant of theta will become x over 2 since x equals 2 secant theta. We see that here. And from our reference triangle, the tangent of theta will become 1/2 the square root of x squared minus 4, which gets substituted in there. All right. This is trigonometric substitution, folks. It's our third technique in what is going to be 4 specific techniques we look at this semester. All right. I will work through a few more of these in class. These 2 examples relate back to case 1 and 2. All right. This works for any integration in any one of these specific forms, folks. And the substitution happens very similarly to what we see above. All the cases are very analogous to one another, right, in their process. It's remembering what case you have. And again, I've done this a long time, and that helps. But I also understand some of the right triangle trigonometry that's happening in the background. And that's what you might want to help wrap your brain around. This doesn't seem very important, but that is what I remember to really try to remember all of this. Right? Respectively. Right? all of this is kind of built on the understanding that the tangent of theta is going to be equal to x over a, which really implies naturally then that x would be equal to a tangent of theta, which gives me this convenient form to be able to sub out with. All right, so that's trig substitution, folks. We're at 25-minute mark. I don't want to be too long with this topic, but I'll give you some more examples in class. And I'll see you in class next time, folks. Hope you're hanging in there. I'll see you in the next video.